Hello to all of you, and thank you for joining this Network Technologies workshop. We are conducting this workshop as part of the GÉANT 5.2 project, and specifically as part of Work Package 6, which is network development. The focus of this workshop is solely on task 1, which works with technologies. And we would like to present to you the 3 specific focus areas that we have. This is quantum technologies, it is fiber sensing, and it is the RARE platform, the router for academia, research, and education. I'm very happy to say that we have 3 experts that will present. We will have short presentations. I think that we will probably be able to answer 1 or 2 questions right after each presentation. But we have also set aside a question and answer session at the very end. So if you have more questions than we can answer right after the presentation, please bear with us and you will have a chance to ask later. You can also put questions in the chat and we will try to get back with you. The slides for each of the presentations are uploaded to the events page, and you can download them from there. We also will make this recording available within the next couple of days in YouTube, and you will have also access via this event page. So let's not lose any more time. Let's start with our first expert. It is Piotr Rydlichowski from PSNC in Poland, and he will talk about our subtasks of quantum technologies.
Thank you, Susanne, for the kind introduction and the meeting today. So, as Susanne mentioned, I would like to share activity that we have within the WP6 connected with the specific aspect of the QKD, quantum key distribution technology, and the interoperability aspect. So, how to connect different systems, different entities within one environment that we can use for our research activities or within different projects. So I would like to focus on 3 aspects today during this presentation. So the QKD interoperability, why we need this, how we approach this, the KMS activity, key management system project that we have ongoing within the group, and we wish to complete and present the results soon. So interoperability. So why we are so focused at the moment on this aspect, especially within the EuroQCI implementation phase. So research and education networks, as probably most of you already know, are either directly or indirectly involved in the EuroQCI projects and initiative. Depending on the scope and aspect, in some areas we provide the infrastructure, in some cases we coordinate, in some cases we provide use cases. But on the multiple levels, either way, all of us are somehow involved in this initiative. What is also very important, if we look at the broad scope, the EuroQCI, is that we have in general 2 segments. The terrestrial QCI, so is fiber-based, optical fiber-based network. So all the quantum key distribution systems and devices are connected with optical fibers, are either shared optical fiber or dedicated dark fiber for the quantum channel, or space QCI, which is in principle free space QKD transmission. It can be between the satellite or ground station, or just on the ground between different places where we're assuming that they have optical visibility. Of course, the space-based QCI is not operational yet, as the satellites are not orbiting and providing the services yet. The goal is to start this proof of concept next year. But from the conceptual point of view and the initiative point of view, it's a crucial part of the infrastructure. Well, with the latest discussion and the vision that the European Commission has, is that the space segment of the EuroQCI, along with the interface to the terrestrial QCI, is planned to have a dedicated part, which is called EU QCI, and the difference is that it also can handle potentially EU secret classification material. So that's why it's a separate entity. Of course, there are still a lot of questions, how it will be, what are the proposed implementation strategies, the ideas, but the discussion is still ongoing. It's not, of course, fixed yet. But from our perspective, so the NRENs and the national QCI, of course, we can operate completely independently of the EU QCI. So this part, which is focused on the EU secret part material. We can, of course, we can complement, we can exchange, given, of course, that we pass all the requirements. We can, that the QCI, national QCI networks can exchange the keys and the services, but it's not needed. If we have a dedicated key management system and interoperable interfaces, we can run independently services between national QCIs, between different national QCIs, completely independently of EU QCI and the Euro QCI. And this is by design. And this is one of the reasons why we are such interested in the open source key management system solutions that are already discussed and developed in NRENs, because it will allow us as the entities to use these services and implement completely on our own infrastructure. As it can be then integrated to different projects and different initiatives, and we do not have the limitations connected with the strict regulations and applications of the EU QCI or Euro QCI. And this is also why the Commission keeps this area open, so the national QCIs can interconnect with each other in multiple ways. And just to summarize this with the latest diagrams from the Euro QCI concept of operation document. So as you can see, the whole Euro QCI ecosystem is composed of the national QCI networks that can be connected between each other completely independently with all the member states, 127. And the secret part, which this EU QCI, is composed of the space segment and the interface to the terrestrial segment, which is governed by so-called quantum hub. And why we need this key management system? Because it allows us to provide the services and establish the services between the over the untrusted network and over the different QCI networks. So why this is why from the NREN point of view and our activities within the WP6 group, it is interesting to further develop and provide these interoperable services. So how, just to summarize how these keys are actually within the QKD's system exchange using the space part. So if member states wish to interconnect between each other, they need to go through the so-called quantum hub, which is the interface between the space and terrestrial part. And then you have this satellite part, which is composed of also the space control center, which is governing the satellite itself, mission control center, which is governing the specific mission-based parameters, and then security operations center, which handles all the security aspects of the whole key exchange and the services exchange. So as you can see, it's quite complicated to go over the whole infrastructure. And it is already governed by the specific rules and interfaces. And if we look at the steps that we need to go through, so first, if we want to exchange the keys, the request from the national service manager, UQCI, is issued, which goes to the Quantum Hub, which is the interface to the space and ground segments. The ground, the user requests are validated within each member states by the security clarification. This is step 2. In the first step, you have the request feasibility check, which is the possibility if the service can be established over the terrestrial QCI, or the space QCI between the member states. Then the setup is being on the 4th stage. The setup is being configured to set up the nodes which actually will hand over and pass the keys, and then the actual, at the end, on the stage 5, the key material is generated and exchanged between the interested member states. So we have, as you can see, we have a lot of interfaces and included parts within the EU QCI. So in order to further develop this for our activities, so within GÉANT and the Android activities, we've decided to set up a test bed and services that will show how different key management systems that govern the QKD, local QKD networks, and the services associated with the QKD network can be interconnected. And using the GÉANT infrastructure, we will set up, we are setting up the layer 3 links that are required to establish the services between the KMS services. Of course, the links themselves can be a dedicated layer 2, layer 1, 2, and layer 3 links. But of course, they can use the existing layer 3 security, layer 3 links, but we need to be sure that for our purpose, it's a secure infrastructure. So we can also secure, for example, if we set up dedicated VPNs for the KMS services, we can use, for example, QKD system to secure the VPNs that link the different key management systems. And we've chosen ETSI GS QKD 020 interface, which is specifically designed to provide QKD interoperable services. So relay and exchange the key over different KMS systems and different QKD vendors. It's a dedicated ETSI interface that was prepared for this kind of applications. But of course, there are different ones. There are other ones, for example, 018, but this one is focused on SDN approach. But for our activities and the equipment that we have, the better choice was 020, because the other ones are more suited to the if you would have the SDN infrastructure setup. But both approaches are standardized and are probably will be used. So just I cannot share I can relate you to the ETSI QKD 020 website. It's not publicly available document, unfortunately, so I cannot share this over the public document, the presentation that will be available. But it is ongoing work within the ETSI work group, and the name is of the group and the work program is DGS QKD 020 Interop KMS work item. However, you can using the website, ETSI website, you can access the API of the interface itself. So it's not that complicated, I would say. It's a straightforward curl document specification. So you can use it either in your equipment, in your application or services designed for the equipment. So it's quite used to download and use the specification. And now how it works. So let's assume that we have two vendors, vendor A and B, where we want to pass on the keys. So within the vendor A, we have the service access entity, which is actually the consumer of the key. So it can be it is interface that application or equipment uses to pull the keys that we want to use in our services. And this interface is communicating using ETSI 014 link to the key management equipment and system that is governing the whole QKD topology. So this is node 1. Within node 2, we have the equipment from vendor A, but also from vendor B. The QKD equipment, of course, it's a pair of equipment. So you have Alice and Bob, the detector and transmitter. In this case, in node 2, we have transmitter. And between the vendors in node 2, we have to schedule so-called external keys calls. So the calls that will allow between the different key management entities that are running on different vendors to request and exchange the keys. So this is this interoperable external key link. And in node 3, we have vendor B, which is mirrored to the configuration in vendor A. And of course, between the same vendors, so within node 1 and 2 and node 2 and 3, vendor 1 and vendor A and vendor B, you have internal links between the key management system that are governed by the specific vendor. So this is the principle that how it works. So now how to implement it. So of course you need to use the specification of ETSI 020 calls. You need to have set up the infrastructure that I will say a little bit at the end. But the most important part actually is the certification. So you need to prepare a set of certificates to authenticate and certify each stage of your connections and what you're actually performing in your system. So as usual, you need to prepare the root certificates, then sign the certificates, put in all the devices. So all servers, they have to present the prepared certificates with the appropriate signatures, and also service authenticate clients by trusting the created services with exactly what was issued in the first stage. So each connection that I showed here, so between the consumer interface, between the KMA and the KMEs, and between the key management entities, you need to have a certified connection. Yes, so you need create those certificates, and this is a part of the activity that we also did. So for the vendor A and for the vendor B, in order to issue all the calls, we need to have this instances between the vendors of the key management systems interconnected and issue the external key calls. And vendor A is the client that needs to offer and present the certificate for vendor V to authenticate. Then the certificate must be signed by the certification authority that vendor B trusts and was signed. And then, for example, vendor A could use the same certificate as the client certificate to be offered to vendor B and has already said within the key management entity the certificate that was signed and can be trusted. And the same for vendor B. So it works in both directions. So it's a quite maybe not very complicated, but you need to be very sure about each step, which connections you actually authenticate. And now how to test it. So based on the specification of C020 QKD interface, you need to issue the get key call, which provides you the key and the key identifier, which is then presented to the service authentication entity, which is actually consumer of the key. And if you compare the exact identifiers of the keys, you are sure that the right keys were exchanged and the right process to authenticate the connection and exchange the keys were set up. So the main principle is to pass the key that was generated between one event within one QKD system to the other QKD system and you can do it over several links. And as you can see, the command is quite simple. So it's a core command. Then you provide the certificates that you prepared for each of the connections, and then you specify the addresses, and the interface, which is actually where the key is being forwarded. And if you have a positive and correct answer, you will receive the key, which is here at the bottom, and the key identifier, and the identifiers between which service entities the keys were being exchanged. So how to put in our case? So for example, let's assume that we have a multiple NRENs, multiple vendors. So site A, B, C, D can belong to the different vendors, and then you wish to exchange the keys and pass all and relay the keys over different KMS system and interfaces. So then you need to set up the KMS, you need to set up the specific links that will serve as a key management system links. You can secure them by VPN, of course. And then based on the procedure that I just described, you can pass the keys between the end entities. Of course, you can stop at intermediate points and sites. But in general, you can skip, you can go between all the other sites. And this is why you can have completely independent architecture for your key management system, regardless of your QCI. So all you need is to set up appropriate KMS connectivity and of course certification of each of the connections. Yeah, and at the end, just to provide the status. So we are working on interconnecting different KMS systems that we have within the work package, set up the layer 3 links, certify the whole setup, and show how the keys are passed on and exchanged. And so this is still under preparation. Yeah, thank you.
So thank you again, Piotr. Let's now move to our second focus area, which is fiber sensing. Here, I'm very happy to be able to present our expert Hanna Mihai from DeiC in Denmark. I see you already started sharing, so the floor is yours, Hanna.
Thank you for the nice introduction. Yeah, my name is Hanna, and I'm just here for a short time. I'm usually just a member of this subtask. Usually the task lead is Chris Etherton, but he's on paternity leave, so I have the honor to present what this subtask has been up to. Yes. I start with an introduction to the world of fiber sensing because I know that a lot of you probably don't know what this is, and that's fine. By the end of the talk, you will have at least an idea. And then I'm going to go deeper into what this subtask is planning to work on for the remaining year. The work in the subtask is split up into three main activities. So technologies, data acquisition and security, and the range of possibilities. This means what can data users do with the data. And then we're also going to do a pilot project. I will give you more details on all of that during the presentation. So we're starting with an introduction to what is fiber sensing. As you all know, fiber cables are almost everywhere, and their main use is to transport data from one point to the other. You can see here an example of the research network in Denmark, which is consisting of both terrestrial and submarine fiber cables connecting the 8 Danish universities with each other. This is managed by the Danish Research Network. As you probably also know, cables also leave countries. In the Nordics, this is then managed by NordUnet, and when we're connecting to the rest of Europe, it's managed by GÉANT. I'm going to give you a quick idea on the terminology that I'm using. Although we're talking about fiber sensing, fibers are normally a part of a multi-core cable, which you can see here on the slide. Changes in the environment of the cable can be detected using the fibers within it. Ideally, with the technology that we're using, the access is granted to a dark fiber, meaning that there's no data transport on it, where you can use any frequency we want to use. However, sometimes you also get only access to a shared spectrum, where we then can only use a specific set of frequencies, because the fiber is shared with other organizations or projects. So we can attach a DAS interrogator to the cable. If it's a submarine cable, then we attach it at the landing stations. With terrestrial cables, it's a bit easier because we have access to the cable. This box that you can see here on the slide then can then measure stretch and strain occurring in the cable. This stretch and strain is caused by the surrounding of the cable being set in motion. This can be done by, for example, an earthquake, or if we are in water, a passing wave or a tsunami that goes over the cable, but also by smaller objects like, for example, whales or ships or submarines. When we're on land, this technology can also be used to monitor infrastructure like train tracks or roads or airplanes. Irregularities in the measured data can then maybe indicate material failure before it actually leads to disaster, which means that we can save time because we can fix things before they break and can therefore avoid longer downtimes of the equipment, like an airplane. And I mean, it's also nice if the airplane doesn't crash because the wheel is broken. We can measure or use fibers to fiber sensing in different ways. There are different ways the cable can be squeezed and stretched, and different sensors can translate this information into data. A DAS interrogator, DAS stands for Distributed Acoustic Sensing, can make use of backscattered light, so-called Rayleigh scattering. Any scattering in general is caused by interaction of light with atomic structures. In our case, it's silica and particles, so impurities in the fiber. To detect and measure stretch stress and strain pressure. SOP, or state of polarization, uses the changes in the state of polarizations of the light to detect anomalies. The changes in SOP are caused by changes in fiber birefringence, so stretch and stress and strain and pressure can be detected and measured, similar to DOS. This here on the slide is a so-called frequency domain plot. This is how our data looks like. And when experts or algorithms, preferably algorithms because we get a lot of data, look at a plot like that, they can know from the horizontal lines that you can see here that they are most likely looking at a ship, because the ship sends out specific vibrations through the water that then leads to compression within the fiber, which the DOS interrogator can interpret into this frequency domain plot. Now we have a rough idea on what fiber sensing can do. So we can now go over to what this fiber sensing subtasks is envisioning for accomplishing over the next year. Last year, fiber sensing was already a part of the GÉANT 5.1 project, and we were represented as an incubator, and since then we have been promoted to a subtask. We have a clear goal to offer fiber sensing as a service within the GÉANT portfolio to other NRANs, but there is a long way to actually get there. For that, we need to figure out how and to what degree GÉANT can do that, and we'll work on that in the coming months. But the first steps towards this have already been taken. We still have a lot to do, prepare documents, but we have formed subgroups to expand the knowledge on fiber sensing within our own subtasks, and we want to reach out to organizations like other NRANs and other projects working with fiber sensing, because there's really a lot going on these days. We have three main activities in our subtask that I've already named in the start. It's technologies, data acquisition and security, and range of possibilities. And additionally, we have a pilot project. We're going to now go through all of the three subgroups. As outlined in the first few slides, in order to do fiber sensing, we need different types of technology. The technology group will this year mainly focus on the latest developments and trends for fiber sensing technologies like DOS and SOP, and follow along the trends presented at the different fiber sensing conferences. On top of that, PSNC has purchased some DOS units and has started testing them. And through this group, like our group, we can assist in benchmarking the different units, which can then help users in purchasing decisions. The outputs that we're planning for this group will be reports on conference participation, a benchmarking report on the experiments that I just talked about. These benchmarking experiments include testing different scenarios, different fiber types, in different environments. There's also a possibility to repeat these benchmarking tests for SOP, because there's also different units that you can, in theory, purchase. If there is enough time and if we get access to SOP units. The group also plans to publish a white paper on best practices for NRANs, considering the available infrastructure, stakeholders, technologies, and use cases. And later in the year, there will be a workshop on the methods and tools that are being developed and used for data analysis. And the group wants to create an overview on the technologies being used in different fiber sensing projects. The second group in the subtask will focus on data acquisition and security. I'm a data management consultant, so we need to talk a little bit about fair data. And I'm going to explain later what that is. We get a lot of data coming from a fiber sensor, and that can be up to 7 terabyte per day per sensor, depending on spatial and temporal resolution. We not only pick up interesting stuff, there's also a lot of noise mixed in within the data, but sometimes you can derive a lot of data from what other people consider noise, and we don't really know yet what it is. For example, different research areas are utilizing different ranges of frequencies and have therefore also different interpretations of what noise is and what data is. We can't just share the raw data from our fiber sensors like cake at a party. Depending on the country involved, you may have to get clearance from the military to release this data. Remember, I told you in the beginning that we can detect not only natural phenomena, but also vessels passing over the cable. You may only be able to share process data, and some data is more sensitive than others. But generally speaking, the security issues for terrestrial data are more manageable than the ones for subsea cables. As a general rule, we want to have the data in a state that is called FAIR, because we like acronyms. FAIR stands for findable, accessible, interoperable, and reusable. Just meaning you should have control over your own data, and you do this for yourself because it's nice to be able to find your data and remember what it means also after not having looked at it for a few months, but also for others that they don't have to write you an email and ask you, what do you mean there? Doesn't make sense. So this is for saving time. This figure is from another project I'm involved in. It shows the data flow for these large amounts of data that are potentially sensitive or maybe just noise. We don't know at this stage. This is from a white paper in the Submerged project that we have been working on for the last few months. This white paper is describing the security architecture for data products produced by fiber sensing, and is supposed to help start a conversation with other fiber sensing projects in order to create a consensus and avoid that we all over and over again reinvent the wheel. It is also meant to help start a conversation with national agencies, like national security agencies, to easily describe what fiber sensing can do, what is potentially sensitive information, and how we can protect the sensitive information. In this figure, you can follow the data from left to right, being in full resolution, only available in a secure computing environment, to vetted researchers and military agencies. The data can then be filtered by the vetted researchers and their algorithms, so it can make it into their scientific publications, but also a reduced data stream can be made available to the wider research community. All data that is not claimed by researchers and stored as FAIR data in discipline-specific repositories that you can see all around the secure data center will be discarded, since storage of data costs money and somebody needs to pay for it, and also data storage is energy intense. This was a very, very quick walkthrough. I did a similar presentation and talked 20 minutes just about this picture, but it's available on Zenodo and has really good descriptions to it, so you can have a look at that afterwards. For the coming month in this activity, we'll want to reach out to other fiber sensing projects and align the ideas on data management and security. There's several other projects working on this issue, so we need to make sure that we don't work in parallel and not do the same thing, or do the same thing while working in parallel. The plan is that we invite them to a workshop where they can present their current workflows for secure data acquisition and storage, but also their thoughts and ideas in case they have not reached that maturity yet. In order to achieve a structured outcome of this workshop, we will have some questions prepared, which can be, do you have a data flow? And if yes, how does it look like? Have you considered the aspect of sensitive data? Because we've seen that some projects have not thought about it, or at least don't talk about it. And do we have plans on who can access the potentially sensitive raw data? How does that work? How to give access? And depending on the outcome of the workshop, we can write a comparison paper or just a simple table that can then be published afterwards. The third group has changed names compared to last year from use cases to range of possibilities in order to capture the difference between the user groups and the different cases they're interested in. Two main examples for users are NRANs, because we can use fiber sensing to monitor our own infrastructure, which is a case we want to monitor our infrastructure, and researchers that can use fiber sensing for a wide range of environmental monitoring, as named before. Examples of that are mammal movement, earthquakes, ocean streams, water temperature, and the list goes on. There's so many possibilities what we can do with that kind of data. The main focus of this group is to collect knowledge on other projects, users, their use cases, and trying to answer questions like, what are the user requirements? What are their knowledge levels usually? What do they want to monitor? This knowledge that's been collected will then be published in shorter and longer documents, like, for example, a table of user requirements and the document they have been working on during the last year, which is the use case document. There's already a draft for that available somewhere. Additionally to that, they will be working on sharing the gathered knowledge through Infoshares, workshops, and conferences. We've talked for all of these three groups about collecting knowledge created in other projects, and here are some of the other projects we are either already in contact with or are planning to contact. So we're talking about Polar Connect, Submerse, GeoInquire, and the Sensei project. All of them can contribute to their in their unique way to the different subtasks. And now we come to the pilot. This is also my last slide. I'm not sure how I'm doing on time. In order for securing success from this, we're planning for progress in the other three groups early on, so the knowledge from there can directly be taken into practice. As for the pilot, GÉANT will deploy their own DAS unit in the second half of 2025 on a cable between England and Ireland. The pilot can be seen as the integrator of all three subgroups, where we utilize the knowledge collected in order to have a successful deployment and can create a well-functioning data and security architecture, making sure data can be shared, stored, and distributed in a secure manner. We can pull on the knowledge that has already been created in other projects like Submerse and organizations involved in these projects like GÉANT and PSNC. That was it from me. If you have any more questions, you're welcome to ask now, but I've also put the emails of the subgroup leads in here, so you can directly ask the questions to the experts.
Let's move now to the third subgroup, last but not least. It's the group that works on RARE, our router for academia, research, and education. Our expert speakers here are Asier, Atutxa, Imatz, and David Franco, both from Bilbao, from the University of the Basque Country.
Good afternoon to everyone, and thank you, Susanne, for the introduction. I am David, and this is my colleague Asier, and we are presenting the RARE, Router for Academia and Research. We are both researchers at the University of the Basque Country, and we participate in the RARE subtask. So this is the content of the presentation. We'll first introduce the rare group, and then we will continue describing the aim of rare, subtask, and we'll present the latest activities that have been carried out in the task, including some relevant use cases that have been developed in the context of rare. And finally, we will highlight the potential future directions and the topics that will be addressed in rare in the following, let's say, months. The rare group develops rare, which is a router for academia and research. And this work takes place under the GÉANT fifth program. The main objective, let's say, is to leverage network programmability to create a high performance and open source routing platform that at the same time meets the requirements of academic and research institutions. This includes support for common networking features, but also with a focus on new use cases and the possibility to test custom development on top of the platform. Well, additional information and details of the rare project could be found in the official website that can be seen here. The subtasks aims at using network programmability to provide a high-performance routing platform known as RARE that is accessible for research and education. And the development of RARE can be split into two main lines, the control plane and the data plane. In addition, or complementary to these lines, RARE also focuses on developing the specific pieces that are required for the integration and deployment of new use cases on top of the platform. So the concept of network programmability is core to this task. And network programmability means that all the network components can be managed and controlled through software applications, using automation tools and programming techniques to make network more flexible and efficient. On the one hand, we have vertical programmability, as it is represented in this picture, which refers to the ability of programming different planes, such as the application plane or the control plane, and also the data plane. So it means extending the programmability through all the planes in the network. And by contrast, we also have the horizontal programmability that pursues an end-to-end programmability of all the elements in the network, including end users or servers and the portions of the network that are necessary for the interconnection. The RARE platform developed in this subtask is a production-ready and fully open source router created for academia and research. And it provides a command line interface to access multiple control plane functions and configure them. RARE supports multiple software and hardware targets. This means RARE provides various data plane implementations such as DPDK or eBPF, and also Tofino switches, which are the most used ones. So RARE provides the most used routing, forwarding, and tunneling functionalities, and probably the high performance provided by the RARE router is its main strength. It has been tested at 100 and also 400 gigs using Tofino and Tofino 2 ASICs. And this means RARE provides a performance comparable to any commercial equipment such as Cisco or Aruba. As an example of a deployment, at the University of the Basque Country, we have two Tofino switches running RARE that are a part of the GP4L, the global P4 laboratory, and they are interconnected to that laboratory through the GÉANT network. Okay, so the latest activities of RARE Group have been focused on development of new use cases that leverage rare routers, and also on the packaging of rare itself to facilitate the installation of the platform on different targets. Now, I give the floor to my colleague Asier, who will provide more details on these activities.
Okay, thank you, David, for the introduction. Yes, so yes, let's start with the first use case, which is the protection of networks against distributed denial of service attacks, or DDoS attacks. Okay, the work carried out in RARE pairs with two other open source projects that are actively developed in other tasks of GÉANT. And the first one, we have the firewall on demand, which focuses on the DDoS mitigation, and then we have NEMO, which consists of DDoS detection and mitigation. The installation and configuration of both tools might be tricky, as it needs at least one router supporting flow spec, and it needs to be located in a network where the DDoS is happening. So the goal of the efforts in our RARE group or subtask are towards the simplification of testing both software projects through the RARE platform and router. So let's start with the first one regarding the firewall on demand project. And the current status of the integration with the RARE platform is, we can say, it's very advanced or well advanced. In fact, currently there is an uncomplicated setup, installation, configuration, and testing of firewall on demand with a testing network based on RARE. The RARE router shares mitigation stats and policies with the centralized firewall on demand through BGP flow spec, so it achieves effective mitigation. And right now, it is possible to perform automated demonstrations of DDoS mitigation with RARE with firewall on demand. So we can say it's accomplished. When it comes to NEMO, the use case, the objective is the same, which is the integration of the software tool in RARE. And in this case, it is the current development is on a similar stage because the setup, installation, configuration, and testing of NEMO it is already accomplished in a testing network based on RARE. This integration is also using BGP flow spec, and it also includes the use of NetFlow. And it is interesting because currently a Moodle course about the integration and testing is underway and will be available very soon. So we will probably release it very soon. Next, we have also another use case which corresponds to the implementation of a 5G UPF in the RARE platform, a 5G user plane function. Okay. And the objective of this is to achieve an affordable UPF system that runs in generic hardware and could be integrated in any virtualized 5G core, which are already some of them available open source. So having a look at the UPF functionalities, which is some kind of router inside the 5G network, it has three main interfaces, each with different protocols that must be developed in order to implement it in the router. So firstly, we have the M4 interface, which connects the UPF with the rest of the core network, and specifically with the session management function, or SMF, which this communication uses the PFCP protocol, which is used by the SMF to send to the UPF the routing preferences and policies that must be followed. So we can say that the SMF installs the rules in the UPF. Second, we also have the M3 interface, which receives data from the 5G base stations and the radio access network, so the users, let's say. This received data is encapsulated using GTP version 2 protocol, and then it is used to send it towards the internet, which is the third interface, which is the N6 interface. Okay. So the most important thing is that at this point of the development, the RAR router obviously implements the IP protocol, which is the one used in the N6 interface. We also developed the PFCP protocol, which is the control plane protocol used in the communication of the N4 interface with the SMF. We are currently polishing the protocol, and the implementation of the GTP version 2 protocol towards the N3 interface is currently ongoing. So we can say that we are finishing our work in this use cases. In this context, we plan to deploy it and test it in an experimental infrastructure that we have in the University of the Basque Country, which is this one that you can see in the slide, which is smart nets for everything. This large infrastructure interconnects 3 main sites that are distant at a distance of about 15 to 20 kilometers from each other. And the whole infrastructure is integrated into the SLICES research infrastructure, or S3, and is also well connected with other architectures, such as the GÉANT network through a point of presence in one of the sites, and also the Spanish NREN, which is Rydlichowski. This infrastructure includes multiple P4 switches, which are the target for our RARE router. And we also have other interesting technologies, such as quantum key distribution and optical interconnection devices, which can be used to deploy other future use cases or other testing solutions that we want to test. And so finally, after analyzing the whole scenario, our plan is to deploy the developed UPF in RARE in one of our sites, which is the one that has the GÉANT and RARE points of presence. So the final objective is to have a standard UPF close to the rest of the 5G core network in one of our sites, and a high performance UPF to route external traffic, which may be like GÉANT traffic, next to the point of presence, so it performs at high data rates. Now we also have another use case, which is the anomaly detection use case. Here, the group has investigated the feasibility of using data plane programming with P4 in anomaly detection in network traffic. The main idea here is that multiple 100 gig streams can be tricky to monitor using rule-based approaches. So if P4 using anomaly approaches could make a coarse filtering, it would be possible to lower the rate of data for further investigation. The implementation here was done using the Planter framework, which is a framework for realizing in-network machine learning based on a data set. Okay. And one of the possible targets for this is P4, where the tensors are implemented using the match action tables in the P4 flow. For this implementation, we used the dataset that you can see here, as this is one of the few clearly labeled datasets, despite it's a bit old, because it has like 7 or 8 years. Rate performance testing was carried out with 100 gig Ethernet tester with focus on small packet sizes. Here, the availability of match action stages is a key limitation in Tofino, which is even more challenging when some stages are needed to extract the key features used for machine learning. In particular, flow information like size and length of flows, as well as packet arrival times, are key features. So to sum up, while the results have room for improvement, there are still interesting steps ahead, ranging from using only feature extraction in P4 with the core machine learning externally to new datasets for training and alternative frameworks such as Taurus, Homunculus, and others that includes FPGA platforms into the flow. Finally, the last use case in the RARE task or subtasks consists of hardware packaging of the router itself in the Tofino platform that we already mentioned. The objective of this is to use the NICs package manager to simplify the installation, and the deployment of Rare platform on Tofino switches, which maybe also, well, it was tricky, now it's probably easier. This provides several benefits, which include one-line deployments with any open source installed environment, seamless upgrades or even rollbacks, and easy to use before development environments, which is very useful. Right now, in this use case, the current work in this field consists of making the transition from the Intel SDE, which was recently or last year discontinued, to its new open source successor called OpenP4 Studio, which is now made available for the community as an open source project. So it's very interesting here also. And finally, to summarize a bit all the presentation and to check some possible future directions, we as a group want to move also forward, because we think that our previous work is very interesting, but we also are always looking for new technologies and new use cases, right? So here, one of our main focuses is to support the research and education community, of course, as this is one of the main pillars of our subtask. And we want to develop more tools and control planes to support the use cases that the research community proposes. For example, using Sonic or microcontrol planes that may be useful for the researchers. We also want to delve into kernel bypassing technologies that we already use, such as DPDK and eBPF, as these technologies provide tools for new functions in the data planes, such as cryptography, that we also find very interesting. Another relevant field of study is to propose completely new use cases. We are not maybe completely new, because we also identified possible work in the integration of FlowSpec v2 to enhance the developments that are already in Rare. But we also identified very interesting to be the integration of quantum communication technologies, such as quantum key distribution that we saw in today's Infoshare, or even post-quantum cryptography, which both of them are considered to be crucial in the advent of quantum computing for the future, right? Also, regarding non-technical work, we also want to support the standardization activities and participate in the definition of future drafts, as well as contribute as much as we can to the community. And in this context, we also want to foster the dissemination of networking, creating documentation that you can check in our website, and also participate in multiple events and conferences that work around network programmability and for example, our Rare router. So this was mostly the presentation. So thank you for listening.
I'd like to thank you all again for joining today. And as I said, we will keep you updated on the work that's ongoing in our projects. And please download the slides, and you will find all the links there, and you can easily also contact us. Have a very nice afternoon, and I see you again in our next Infoshare. Bye-bye.